covering the topic of estimating the derivative of a signal from sample data, more specifically samples of that signal. All right, so a few things you need to know going into this. We're going to use this method and technique in our quest to do symbol synchronization. Okay, so that's going to show up in a different video. All right, the other thing that you need to know is that this applies for band-limited data. If you have band-limited data and you're sampling it fast enough, you'll have samples that you can use to produce estimates of the derivative. Okay? It also requires that you have a block of data. You'll need a certain number of samples in front of the point in time, in advanced in front of time of the point that you're trying to take the derivative of, and you'll need a certain number of samples prior in the past. Okay? So you have to have both those things true before you can make an estimate. And then you should also be aware that in general, if you have samples but there's some noise added into those samples, that will call into question whether or not the data is truly band limited. Okay, adding high frequency noise will probably mess up the estimates, and so estimating derivatives with noisy data is well known to be a difficult thing to do. Okay, so with that, let's move forward. All right, so here's what we're talking about. We have samples. So I've drawn a picture of the samples, and what we're trying to do is we're trying to estimate the derivative. So when we first look at this, we're thinking, well, that doesn't even make sense. What do you mean by a derivative? Derivative is a slope through a given point. That could have, what does it even mean to have a slope at a given point? And so the context that you have for this is that these samples came from a band-limited process. Okay, so if I take this and I move it and show that it comes from this band-limited signal, it makes more sense to talk about what does it mean to have a derivative. Okay, and so what we're looking at in this case is how do I get the slope at any sample value or even a fraction of a sample, like what happens right here. What is the slope of the original function at this midway point between two samples? All right, so at first you're thinking, wow, how could you do that? Well, if you go back to Sinc interpolation, since we can interpolate to find the original signal here, all right, here's the original signal. Since we can interpolate to find that, we can use that method to estimate the derivative. Okay, so here's how the math on this works. This is derivative estimation from sampled data. Okay, so let's start. What we're going to try to do here is we're looking at dx of t dt. And we know from the definition of a derivative that that's the limit as delta, some parameter delta, goes to 0, of x of t plus delta minus x of t minus delta. So you take a little step in time forward, take that value, take a little step in time backwards, take that value, take that difference, and then you divide by 2 delta. So what you learn in calculus is that if you let this limit as delta goes to 0, you will get, in fact, the derivative of the signal, assuming that derivative exists. Okay? So what we know from sample data is that we replace t with nt. Okay, so just doing that step, evaluating it at t equals n cap t, we would have this as our expression for the derivative. Well, from here, and oh, by the way, what we know is that t is the sampling period. And we are going to, on the next step, let capital delta be lowercase delta times cap t. All right, so from there, we can plug in. So capital delta becomes delta t, and we're going to let that product go to 0. Remember, t is fixed, so let delta goes to 0 forces the quantity delta t to 0. Okay, so then we have x sampled at n plus delta, and so the reason I made this definition is so I could factor out t. Okay, so we have x of n plus delta times t minus x of n minus delta times t. Okay, and then that would be divided by 2 cap delta, but cap delta is lowercase delta times cap t. Okay, so the nice thing about this mathematical expression is that you can view n plus delta as a sample plus some fraction of a sample. So for example, if we were looking at n naught equal, say, 16, if I made delta equal 0.25, then n naught plus delta is 16.25, and so we're looking at a fraction of a sample, 1/4 of the way between sample number 16 and sample number 17. Okay, so it's easy to think about it in those terms. Okay, so from here, we can drop the limit, all right, and we will have an approximation. Okay, so we're going to choose a small value of delta when we actually implement this. All right, we're going to do x. We're using square brackets here, so remember, square brackets mean discrete signals. Okay, so x of n plus delta, x of n minus delta, those are the samples divided by 2 delta cap t. All right, so technically we don't have access to either one of these values, n plus delta, n minus delta. That's where we use the interpolation step. Okay, so from here I can just rewrite this a little bit. N plus delta minus x of n minus delta divided by 2 delta, and t in the denominator is the same thing as having fs in the numerator. Okay, so we scale this by fs to get an approximation of the derivative. Okay, so in the next portion of this video, what we're going to do is we are going to go over some of the code that I wrote for a previous interpolation example. We've already seen this once in a video, but I'm going to go over it with you again to make sure you're on the same page. We're going to use my interp2 as an M file to do the interpolation. It turns out I discovered a numerical error in the code from the TB MATLAB book. He used the round function where he should have used a floor function, which gives you an error at the midway point between samples. Okay, so my interp2 fixes that problem, so be sure and use that. So I'm going to walk through the code, and feel free to pull up this video whenever you're trying to work the homework assignment. I'd like to walk through the code. Now I'm going to ask you to produce similar code for a homework assignment, so hopefully this will be helpful for you. So step 1, I'm just closing all the figures. You end up running these things multiple times, and sometimes it creates a bunch of stray figures that show up all over your computer. So let's close all the figures. The first thing I do is I set the sampling rate. That's in samples per second. Right, then I'm going to take 60 samples of this signal. The signal is down here, defined down here, is simply a 100 hertz sine wave, so sine of 2 pi 100 t, t is in seconds. Okay, I'm taking 60 samples, 1 through 60. It's important to start at 1. Okay, because otherwise your plots get a little bit off because MATLAB indices start at 1. All right, so I'm not going to go into the details on that. Just take that on faith. All right. Next, we generate the samples. Y of n is sine 2 pi 100, and then we replace t with n divided by fs. Okay, so n is the sample number. All right, so if n is in samples and fs is in samples per second, okay, I'm sorry, if n is an integer and fs is in samples per second, then the units here turn out to be samples for yn. Okay, next, what I want to do is figure out what is the maximum time that 60 samples ends up taking if you sample every 1 over fs. Okay, so you take the maximum of n, which is, in this case is 60, and you divide by fs, and that gives you the maximum time in seconds. All right, so from what I do here, this step, the goal here is to generate a plot, an accurate plot of the signal that we're trying to do interpolation on. Okay, so a rule of thumb that I use is if you take the Nyquist sampling rate of a signal and you multiply that by 10, not the Nyquist rate, but the sampling rate, assuming you're sampling at the Nyquist rate or more, if you multiply by 10, you're guaranteed to have some nice looking plots. Now keep in mind, plotting programs, what they do is they connect points on a plot with straight lines, and so if those points are close enough together, the straight lines make it look like an accurate representation of the signal. All right, so I define t, I take yt to be the representation of the signal. All right, so I'm going to now plot these things. All right, so this particular code is to plot only a few samples, right? We don't need to look at the whole signal. We're just trying to zero in on what happens at the sample level when we do interpolation. Okay, so we're going to plot samples 15 through 20. All right, so the n values are 15 through 20. The samples of the signal are 15 through 20. I'm going to make this blue and set a line width of 2. All these are just formatting things for the stem plot. I'm going to then hold that plot, okay, and next I'm going to do a trick for making the accurate plot of the signal line up with the stem plot. Okay, so what I do here is I start looking at t times fs. Remember, t is a time vector and it's in seconds. All right, so if I look at the product, t times fs, we're using that as the time axis. That turns out to be in samples. One way to think of that is if you take t, which is in seconds, and you multiply by the sampling rate, which is samples per second, then the overall result turns out to be in samples. Okay? Now the catch here is we're used to thinking of samples as being spaced apart by integers, but because we're doing this kind of different interpolation problem, it's possible to have fractional samples. In fact, that's the whole point. All right, we want to see what happens at, for example, sample 16.5. All right, halfway between sample 16 and sample 17. All right, so it's kind of a different thing, but that's how we can handle that. So the find command, what it does is it looks for the index values of the vector t such that t times fs is greater than 15 and t times fs is less than 20. We capture all those index values, all right? So then when I make the plot, I just need to plot t using those index values from the find command. Okay, so that's what I do in the next step. I've already held that plot, so at that point, everything will line up, okay? The next few lines of code, you don't really need to know every detail about how that works, but I messed around with this a little bit to make a legend, to put it on a title, to make the plot look a little nicer. Okay, so that's what that section of code is for. Next, what I want to do is actually plot some interpolated values. Okay, so to make that happen, I make an empty array called yInterp. I choose the values that I want to interpolate over. I'm going to go from, let's go on out to 20. From 15 to 20 in steps of 0.1. All right, so that's the vector ns, 15 to 20 in steps of 0.1. I'm going to make a for loop that sums over that vector, okay? And so you see every time what I'm doing is I'm growing a vector, I stuff the answer at the end, okay? So initially it's empty, the first time through the loop I get the value that's interpolated for sample 15, okay? It showed a 19 because it's already run, but anyway, you get the point.
after we're done, we will have interpolate values for input samples 15 through 20 in steps of 0.1. Okay, so from there, I've already defined this ns vector. I can plot ns and y-interp. I put something down to show the markers. Again, this is formatting, but I'm basically plotting these things and setting my legend. Okay, so that takes care of the first part where we are looking at an interpolated signal. The next part, what I want to do is compare what happens when I am using interpolation to estimate the derivative of a signal. Okay, so we've already shown a video about that. So I went ahead and took the derivative of sine of 2 pi 100t. This turns out to be the mathematical expression for the derivative. Okay, so this next line of code is to plot it. Okay, here's the derivative, and here's the code that will plot this. It's going to plot it in a separate figure. Okay, so we're separating out the original signal and the estimate of the derivative. Okay, so what I'm going to do is I'm going to go in steps of 0.1 from 15 out to 20. I'm doing the code slightly differently, but you get the idea. And then we went through the mathematics of this. I'm going to choose a delta to be relatively small, 0.001 in this case, and I'm going to interpolate. Okay, so these are my signal values. Remember, way back at the top of the code, yn is just samples of that 100 hertz sine wave. Okay, for n naught, remember n naught is starting at 15, goes to 15.1, 15.2, and so forth. For each value of n naught, I add delta and I subtract delta, and I'm doing an interpolation for points 2 and points 1. You get the idea. So from there, we talked about the derivation of this. You just take the difference between the two deltas, you divide by delta, and you multiply by fs. And that will give you an estimate of the derivative based only on samples of the original signal. Okay, so then I'm going to plot that, and you'll end up seeing two figures, one with the plot of the interpolated samples of the original signal, and the second one with a plot of the derivative using this two-step approach to estimate the derivative. Okay, so we'll run that code. All right, and so figure 2 is the derivative. Figure 1 is the one I had with the formatting. All right, so you see the faint blue line here, that's the original sine wave. That looks like a sine wave. We're restricting the samples between 15 and 20. You get what I'm saying, right? That if you just look at the stem plot, it's hard to tell if that's a sine wave. All right, that's a consequence of ideal sampling. The ideal reconstructor is trying to put a sum of sinc functions between those sample values, and so we're used to sort of connecting this with straight lines visually when we make a plot, and that's not what actually happens with ideal reconstruction. We sum up sinc functions. Okay, so you can see the little x's show the interpolated values. Again, not to belabor the point, but the significance of this is each of these fractional sample points. Okay, so here's sample 15, here's sample 15.1, here's sample 15.2. I'm reading the x-axis down here. All these were estimated from just the blue stem values. Okay, nothing else. You had to have 12 samples in advance out into the future and 12 samples back in the past to make these estimates, but based on those samples, you can come up with accurate estimates of the original signal. Okay, I can zoom in here and I can see, it's not perfect. It's a little bit of numerical error, okay, but it's pretty good. It does the job for what we need it to do. Okay, moving to figure 2. Figure 2 is the same idea, only this time the blue line represents the derivative of derivative of sine. All right, so we mathematically calculated that, and we can plot that with the blue line. And you see this estimate works reasonably well also, and you can estimate the derivative of the original function by just using Sinc interpolation. Okay, so again, there's some limitations on this. The signal has to be band limited. The signal shouldn't be noisy. It's hard to do these differences. If it's a noisy signal, you tend to get junk back. Okay, so, and by the way, if it's a noisy signal, it's probably not band limited. So that, all bets are off in that case. But so what you see here is it's possible to do this derivative estimate of the original analog signal with only the sample values. Okay, so where we're going to go from here is we're going to use this approach to do optimal symbol synchronization. Okay, so that'll be the subject of the next few videos.